Okay, welcome back to another video, and today we're going to talk about normality and the Central Limit Theorem. And so this is going to be a continuation of the discussion we had about sampling distributions. And last time we had introduced what sampling distributions were, and today we're going to talk about why they're useful and how we actually use them. And so we'll do a quick recap. And so typically a question that we might seek to answer with sampling distributions is one like this. Is our sample data and our sample statistic consistent with what we would expect to see from samples that really did come from a population with certain characteristics? And I know that might seem a little convoluted and confusing, so let's talk about an actual example, and I think it'll make more sense. So an example of this might be that we think at the population level that the average hours of sleep for American newborn boys is 7 hours. And so we might write that as mu, our population mean, equals 7. So basically our group of interest is all American newborn boys, and we think our hypothesis is that the average number of hours of sleep that they get is 7. So that's our population parameter, and our hypothesis is that it's 7, but it's actually unknown. We don't know for sure what the average number of hours of sleep of American newborns is. Our hypothesis is that the sample average is 7. Or sorry, not the sample average, the population mean is 7. So again, just to be clear, because I screwed that up a second ago, our hypothesis is that the population mean is 7, but that is unknown. We don't actually have access to all of the hours of sleep recorded for every American newborn boy. So to answer this question and test this hypothesis, we gather a random sample of, say, 200 newborn boys, and we record their sleep habits. And our sample average just happens to be 6.3 hours. So on average, the 200 newborn American baby boys in our sample sleep an average of 6.3 hours. And so we might write that as X bar, our sample average, equals 6.3. And so our question is a sample average of 6.3 hours a value that we might reasonably expect from a population where the mean really is 7 hours? In other words, is our sample average that we got, our sample statistic of 6.3 hours, is that value consistent with what we would expect to see from a population where the underlying or true mean really is 7? And so our approach is going to be that we're going to compare our observed sample average of 6.3 to the sampling distribution for the mean, which I like to refer to as the distribution of sample means because I think it makes more sense. And we're going to compare again our sample average to this distribution of sample means for a population with a mean of 7. So in other words, we're going to compare our observed sample average of 6.3 to the distribution of the sample means that we would observe if we drew samples over and over and over again from a population with a mean of 7. And if you still need some clarification on what exactly that means or what that would look like, please watch the previous video on sampling distributions, especially the part where I go over that interactive website visualization where you can basically visualize what a sampling distribution looks like. So again, if this is confusing to you, please make sure to check out that video first. I will discuss it again in a few minutes here, so you can stick with me. But again, if you're just completely lost, check out that previous video. But the issue with sampling distributions, though, so again, remember, sampling distributions are conceptual, right? They're the distribution of sample statistics that we would see if we took, samples over and over and over and over again from our population, right? But they're conceptual because we can't actually draw a bajillion samples from the population. And the sampling distributions are going to be different based on whatever the underlying population characteristics are. So in other words, if your population mean is 7, for instance, and you have a population standard deviation of 2, then the distribution of sample means is going to look different for that population than it would if the standard deviation was 4, or if the mean was 8, or whatever the case may be, right? The point is that whatever the characteristics of the underlying population really are, that's going to impact what the sampling distribution is going to look like. So there's going to be different sampling distributions for whatever the characteristics of your population are. And I highly encourage you to play with that sampling app that we went over in the last video, because what you can do is you can try simulating populations with different characteristics, different shapes, different averages, different standard deviations, and what you can do is you can see how the sampling distributions change based on those characteristics. So again, the main thing to take away here is that the sampling distributions will be different for each specific population and each specific population characteristic. However, the central limit theorem tells us that there are certain properties of sampling distributions that we can know without actually having access to the population and having access to all these, infinite number of samples. So in other words, right, even though we can't actually draw a bajillion samples from the population, the central limit theorem is a theory that is going to help us figure out what the distribution of sample means will look like for any population. And it's going to tell us the characteristics of that sampling distribution, provided that a few conditions are met. So in other words, a few things have to be true in order for the central limit theorem to be able to help us basically figure out what the sampling distribution for the mean is going to look like. And this will make more sense in a few minutes. So at a really high level, again, we have sample data. We want to compare our sample statistic to the sampling distribution, but we don't actually have access to draw a bajillion different samples to kind of simulate our own sampling distribution every single time. So we need a way of having access to the sampling distribution, or at least certain characteristics of it, in order to compare our observed data to that sampling distribution. And so again, this is an image I used in the previous video. If we think about this population right here where my cursor is, each of these gray dots might represent all of the newborn baby boys, American newborn baby boys in the population, right? And the mean might be 7 hours of sleep. But then when we draw samples, each sample corresponds to a selection of a few of the observations from the population, not all of them. And the different colored dots here represent different samples and different sample statistics we might get. So our first sample, we might get a sample average of 6.3 hours, just like we got. But then the second time, we might get 5.2, we might get 9.2, we might get 4.6. This is all sampling error. And so we can look at this visual down here, where if this represents our population, all of these little X's might represent different observations of different, baby boys in the population and the number of hours of sleep that they get. Okay, so this represents the distribution of the number of hours of sleep at the population level, and it has its own mean mu. But then we can draw samples of a given sample size, which we call n. So we draw samples of size n, and each time we calculate the sample average x bar. And so then we can plot the sampling distribution of the mean, or the distribution of those sample means. And the one highlighted in green is the actual sample mean that we might happen to get. And then the ones in the background are all of the different sample means that we might get if we sample from this population. So just another visual of what the sampling distribution for the mean might look like and what it means conceptually. And so our goal, right, is to compare our actual observed sample mean to this sampling distribution for the mean to see whether or not the value that we actually got is reasonable and kind of falls within the values that we would expect to get when we sample from the population over and over again. Before we go any further with the central limit theorem, we need to talk about the normal distribution real quick. So if observations follow a normal distribution, the reason we like this is because we can make probabilistic statements with just the mean, mu, and the standard deviation, sigma. So in other words, with just these two parameters, just knowing just the mean and the standard deviation, that's all we need to know to figure out the entire shape of this distribution and how all of these observations are going to be distributed. And the reason this is important is because if we look over here on the left, basically what this is showing us is if we have a population that's normally distributed, or values that are normally distributed, and they have a mean mu and a standard deviation sigma, then we know what percent of our values are going to fall roughly within 1 standard deviation of our mean, 2 standard deviations of our mean, and so on and so forth. And so we can figure out the probability that a given value will fall within a certain range. Because if we know the mean and we know the standard deviation, then we can take any value that we're interested in and we can say, okay, well, this value is really 2 standard deviations above its mean, and these values are distributed normally, so I know that basically there is a blah, blah, blah probability of getting this value, or there is a certain probability that our values will fall between this number and that number. And so the normal distribution is really powerful because with knowing just the mean and the standard deviation, that's all we need to know to be able to figure out what percent of values will fall within a certain range. And so if you think back to our statement about our problem where we have the observed numbers of hours of sleep, the average is 6.3, right? And we're interested in whether or not our population mean is 7 hours of sleep in the population. Well, we can use that information if we know the mean, if we really did know the mean and we really did know the standard deviation, we could use that information to figure out what the probability of actually observing a sample average of 6.3 is, given a underlying mean of 7 and a standard deviation of whatever it may be, right? So the point is that in that example where we're interested in determining the average hours of sleep for newborn baby American boys, if we did know the mean and we did know the standard deviation, then we could figure out the probability of getting a certain number of hours of sleep given this population average and this population standard deviation. And over here on the right, this is just to show you that if you know the mean and you know the standard deviation or the variance, which is just sigma squared, the standard deviation squared, if you know the mean and the standard deviation, then that is enough to basically know exactly how the distribution is going to be shaped and how the values are going to be distributed. So we can see here that as our standard deviation gets smaller, this blue line right here, the distribution is going to be more peaked and the values are going to fall within a tighter range. Whereas if we look at the extreme with this orange or gold line, where our standard deviation and our variance is much larger, then our values are going to be much more spread out and we're not going to be as certain. And you can see that with these different colors, right, just knowing the mean and the standard deviation is enough to have access to pretty much everything we need to know. And so real quick, to give an example of what this might look like, if we do know the population mean, so let's just say it is 8 and the standard deviation is 3, so let's say we really did know those things, then we could say, okay, well, what's the probability of observing a value of 6.3 or less if the mean is 8 and the standard deviation is 3? So in other words, our population mean hours of sleep really was 8 and the standard deviation was 3 hours. What would be the probability of observing a value of 6.3 or less if that mean was 8 and that standard deviation was 3? And so what we can do is we can convert our raw score of 6.3 to what's called a z-score, and then we can use the standard normal curve to answer this question. And so what the standard normal curve is it just is a normal distribution with a mean of 0 and a standard deviation of 1. Because otherwise, if we didn't convert our raw score to a standard normal score or a z-score, we would have to basically have a different normal distribution charted for every possible combination of a given mean and a given standard deviation. Because remember, if we go back to this, we see that with every combination of a different mean and a different standard deviation, our normal distribution changes both its shape and its location. And so if we didn't have things on a standard normal scale, then every time we had a different population mean and a different standard deviation, we would need to consult a different chart of normal distributions in order to figure out what areas are going to fall or what values are going to fall between certain limits, right? So the point is that instead of having to basically consult a different table and a different graph every time we have a different mean and standard deviation, we try to standardize things and put them on a standard normal scale. And so the way we do that is basically we take our value and we subtract whatever the mean is from it, and then we divide it by the standard deviation. So if you think about values that are distributed normally with a mean of 8 and a standard deviation of 3, like we have in our example, well, if we subtract that mean of 8 from our value and we divide it by the standard deviation, if we did that for every possible score in the distribution, then those scores would no longer be distributed normally around a mean of 8 and a standard deviation of 3. Instead, they would be distributed normally around a mean of 0 and a standard deviation of 1. So when we convert scores into z-scores, what we're doing is we are basically changing our raw scores onto a scale where they are relative to a mean of 0 and a standard deviation of 1. And so that's all a z-score is. We're taking a raw score and converting it to a score on a standard scale. And so the way this looks is the formula is a z-score is equal to our raw score x minus the mean mu divided by the standard deviation, which in this case would be 6.3 minus 8 divided by 3. Do the math, and that gives us a z-score of negative 0.57. So our raw score of 6.3, if it comes from a distribution that's normally distributed with a mean of 8 and a standard deviation of 3, that raw score is equivalent to a z-score or a standard normal score of negative 0.57. And all that means is that our score lies a little over or a little under half of a standard deviation below its mean. And so then we compare our z-score that should say a z-score of negative 0.57, not a z-score of 6.3, sorry. Now we compare our z-score of negative 0.57 to the standard normal distribution, the z distribution. So again, ignore that typo. That should say we compare our z-score of negative 0.57 to the standard normal distribution. And if we look over here at our curve right here, this is our standard normal curve. Well, right where my cursor is, this represents a z-score of negative 0.5. And what you can see is that half the scores fall above a z-score of 0 and half fall below 0, of course. And then when we move out between 0 and negative 0.5, that's about 19%. So if you do 19% plus the 50% that falls to the right of a z-score of 0, 50% plus 19%, that's roughly 69%, call it 70%. The point is that roughly 30% of the values are going to fall to the left of a z-score of negative 0.5, which is the same thing as saying 30% of the values will fall below a z-score of negative 0.5 roughly. And so the answer to our question is that there is roughly a 30% chance of observing a value of 6.3 or less if the scores are distributed normally and the mean is 8 and the standard deviation is 3. And so to take this back to a high level, right, the reason we like the normal distribution is because if we know the mean and we know the standard deviation, we can easily convert our scores such that we are able to figure out exactly what the probability of observing certain values is between a certain range or above and below a certain value. Whatever the case may be, we can easily figure out and make probabilistic statements about ranges of values or certain values. And with today's computing power, right, a lot of times you can just enter in these numbers right away and you don't have to consult different charts or tables, right? But back in the day, this is why the standard normal curve and the standard normal distribution was so powerful, was because you only needed one single chart with one single set of tables and z-scores, right? A lot of you might still have professors or teachers or remember having those teachers that made you look in books to find the area under curves, right? And so that's a hold back to the days when we didn't have computer programs where all we had to do was enter in our mean, our standard deviation, our value, and boom, it spits out a number, right? That's basically the same thing as what's going on in the background is we are comparing those values to a standard normal distribution. Okay, so connecting this back to sampling distributions. This shows us why we like it when sampling distributions are normal. We can calculate the probability of observing any specific sample average or range of sample averages by knowing just the mean and standard deviation of the normal distribution. Of the sampling distribution. So again, I'll say that again. If the sampling distribution is normal, then if we know the mean of that sampling distribution and the standard deviation of that sampling distribution, we can then calculate the probability of observing any specific sample average or range of sample averages. Because remember, our whole goal was to use the sampling distribution to compare our observed actual sample average that we got to the distribution of sample averages that we would expect given a certain population. But we didn't have access to every possible sampling distribution for every possible population. But here's the thing, if we know that the sampling distribution is normal, then we don't need the entire distribution. All we need is its mean and standard deviation. So I'll say it again, if we know that the sampling distribution is normal, or the distribution of sample means is normal, then all we need to know is the mean and standard deviation of that sampling distribution, and then we can compare our observed values, our observed sample statistics, to that sampling distribution and make those probabilistic statements that we're interested in. We can make statements like the probability of a sample average of 6.3 or less coming from a population with a mean of this or that is this amount, right? Because we are able to directly interpret the sampling distribution for the mean for that population. And this is all through the central limit theorem. The central limit theorem tells us the characteristics of the sampling distribution for the mean that we need. Specifically, the central limit theorem tells us that the distribution of sample means will be normally distributed, and it will have a mean equal to the population mean, and a standard deviation or a standard error equal to the population standard deviation divided by the square root of your sample size. So I know these symbols probably look like Greek. What this represents, this mu with the little x bar, that is the mean of the sampling distribution for the sample means, or the mean of the distribution of sample means. And it's saying that that mean of that sampling distribution for the mean is equal to mu x, which is the mean of the population distribution, or the mean of the distribution of x in the population. So again, our sampling distribution will have a mean equal to the population mean, and it will have a standard error or a standard deviation itself that's equal to the population standard deviation divided by the square root of your sample size. And so we've just seen that, okay, the central limit theorem is going to help us know that our sampling distribution is normally distributed, and it's going to tell us what the mean of that sampling distribution is, and it's going to tell us what the standard deviation of that sampling distribution is. And all we need to do is we just need to know our population mean and our population standard deviation. And most importantly, this will be true regardless of the population shape, as long as our sample size is large enough. So in other words, as our sample size n approaches infinity, or as our sample size gets larger and larger and larger, the central limit theorem is going to be true even if our population isn't normally distributed. Now, if our population is normally distributed, then it doesn't matter what our sample size is. That sampling distribution for the mean will be normally distributed regardless. But if our population isn't normal, even if it looks skewed, right, the central limit theorem tells us that as long as the samples we're drawing are large enough, then that sampling distribution will be normal, and it will have a mean equal to the population mean, with a standard error equal to the standard deviation of the population divided by the square root of n. And so ignore all the text and just focus on the images for a minute. So right here at the top where my cursor is, this represents a population where we see all these little x's in the background. These are just all the different values in the population. This mean mu represents the population mean, and the sigma represents the spread or the standard deviation of that population. So it's just telling us that as we draw samples of size n and we calculate the sample average x bar, then we know that the sampling distribution for the mean will be distributed normally, right? See that normal shape in the background? And it's going to have a standard deviation itself, or the standard error, that's equal to that population standard deviation divided by the square root of our sample size. And so what you can see is, because the sample size is on the bottom of that formula for the standard deviation of the sampling distribution, that means that as our sample size gets bigger and bigger and bigger, then the standard deviation of the sampling distribution is going to get smaller and smaller and smaller, which means it's going to be less and less spread out. So the larger our sample size, the more certainty we're going to have about our estimate, because that sampling distribution is going to be tighter and tighter. And so if we look at the bottom image, what this shows us up in the top row, these all represent different shaped populations. And then as you go down with each column, it shows us a variety of different sample sizes that we could have, and it shows us the distribution of the sample mean, or the sampling distribution for the sample mean, as we look at different sample sizes and different population shapes. So we'll start with the normal one. As you can see, even when you only have a very small sample size, a sample size of 3, that sampling distribution is going to be normal regardless, because the population was normal. And then as the sample size gets bigger, that sampling distribution will get tighter and tighter. But then even if you have a skewed distribution in the population, well, that sampling distribution, it might not be perfectly normal at first when we have a small sample size, right? You can see how the sampling distribution is kind of skewed when n equals 3, when the sample size is 3. But as that sample size increases, that sampling distribution gets more and more normal, and it gets tighter and tighter. And even if our population is uniform or irregular, so highly non-normal, as that sample size increases, so as we proceed down in these columns, we see that the distribution of sample means is still going to be normal. And so this is what's so powerful about the central limit theorem, is that we can see from these graphics here that regardless of the shape of our parent population, as long as our sample size is large enough, then we know that sampling distribution is going to be more and more normally distributed, and it is going to have a mean that's lined up with the population mean, right? See how the red line is perfectly aligned? And it's going to have a standard deviation that's equal to the standard deviation of the population divided by the square root of n. And so over here, now we'll go over the text I have written. And so that first bullet just says if the population is normally distributed, then the sampling distribution for the mean will be normal automatically. And then if it's not normally distributed, then the sampling distribution for the mean will still be normal, and it'll have a specific mean and a specific standard deviation as long as our sample size is large enough. The larger that sample size n is, the more normal the distribution of sample means will be, and the tighter it'll be. Exactly how large the sample size needs to be depends on the population shape. The more non-normal your population, the larger your sample size needs to be in order for this theorem to take hold. So let's put it all together. We have a sample of 200 newborn boys, n equals 200, who sleep an average of 6.3 hours per night. So the sample average x bar equals 6.3. Our hypothesis is that newborn American boys on average sleep 8 hours per night, or mu equals 8. Again, mu is unknown, but our hypothesis is that it's 8. We know that the standard deviation of newborn boys in the population is 3 hours, and that should say sigma equals 3. Again, my apologies about the typos. So just to clarify, in this hypothetical example, our sample average is known, that is observed. That sample average is 6.3 hours per night. The hypothesis is that the population mean, mu, is 8. So mu is unknown, but our hypothesis is that it's 8. We know in this hypothetical example that the standard deviation of newborn boys in the population is 3. So that should say sigma equals 3. So x bar is known, it's 6.3. Mu is unknown, but we think it's 8. Sigma is known in this example, and it's 3. And that's just for this example. So what would the probability of getting a sample average of 6.3 or less be if the population average was 8 and the standard deviation was 3? So that's just the question that we're seeking to answer. And we can write that in notation as probability P that x bar is less than or equal to 6.3 given that x in the values of the newborn baby boy's sleep, x, that's what x represents, is normal in the population, normally distributed, with a population mean of 8 and a standard deviation of 3. Okay? Well, the central limit theorem tells us that the sample average itself, x bar, is going to be normally distributed around its own mean of 8 with its own standard deviation of 3, which was the population standard deviation, divided by the square root of 200, which was in our sample size. So again, I just got these values from plugging in the mean, or population mean of 8, and the sample size of n of 200, and the population standard deviation, sigma, of 3. And so the central limit theorem told us that our sample average, or the sampling distribution for the mean, will be distributed normally around its own mean of 8 and its own standard deviation of 3 divided by the square root of 200. And so we can convert our sample average to a z-score like we did earlier with regular values, and we can say z equals x bar minus mu over its standard deviation, which the standard deviation in this case, because it's a sample average we're dealing with, the standard deviation of the sample averages, or the standard error of the sample mean, or the standard deviation of the sampling distribution, those all mean the same thing. That's sigma over the square root of n. So again, our z-score is going to be x bar minus mu over the population standard deviation over the square root of n. So when we plug in our values, we get 6.3 minus 8 over 3 divided by the square root of 200. This works out to negative 1.7 over 0.21, which gives us a z-score of negative 8.02. So our sample average of 6.3 equates to a z-score of negative 8.02. So then we consult either our tables or a statistical software that can chart the z distribution, and it tells us that the probability of getting a z-score of less than negative 8.02 is tiny. It's basically 0. And you can see that in this graphic of the standard normal distribution. It's usually only charted out to maybe 4 standard deviations above or below the mean. And ours of negative 8 is so far off the screen that it's virtually almost a infinitesimally small probability, so a probability close to 0. So what does this mean? Well, it's very, very unlikely that the population mean truly is 8. We can't say that for sure. All we can say is that the probability of getting a sample average of 6.3 from a population where the mean really is 8 is very, 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 very small. So it's very unlikely that the population mean really is 8. But our probability is not directly interpretable in terms of the probability that the population average is 8, right? Our probability is not interpretable that way. Our probability is only interpretable as the probability of getting a sample average of 6.3 from a population with a mean of 8 and a standard deviation of 3. So just to be clear, we are not making direct probability statements about the population average. We're making direct probability statements about the probability of getting a sample average if the population had these characteristics. So we can say that the population parameter or the population value is likely or not, but we can't say firmly what the probability is that it's a certain value. And so I'm not going to go over all of this, but you're definitely free to copy this table. It's really, really useful. I will go over these 2 bullets on the left. So the recap is that if we know the population mean and population standard deviation, and our sample size is large enough, the central limit theorem gives us the shape, mean, and standard deviation of the distribution of sample means that would come from that population. We can then use that normal distribution of sample means to compare our observed sample mean against in order to determine the likelihood that our sample average was drawn from a population like the one we hypothesized. And so in this table over here, we have a column that talks about population terminology and definitions, sample terminology, and the sampling distribution terminology. And I'm not going to go over all of this, but this is a really, really useful table, and I highly recommend you check it out. As always, the PowerPoint can be found on my GitHub page, and for those of you not familiar with GitHub, you just click on the link in my description, and then you go to the folder that says Statistical Concepts, and then download the PowerPoint that says, I think it's called Central Limit Theorem and Normality or something like that. But definitely please feel free to download this PowerPoint, and I'll make the changes to correct those typos by the time you've watched the video. So thanks as always for watching, and I hope you all have a great day.